In this lecture, we are going to look at some code for how to deal with missing data, as well as continue looking at some other basics of dealing with financial data. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. Note that this is a continuation of the same notebook we'd been looking at previously. So first, we're going to start by using our close prices dataset and calling the plot function directly on the series given by the IBM column. Note that there is some missing data here, as you can see from the gaps in the line chart. However, recall that this may be because of how we created our dataset. We created the dataset by creating a date range, which included all the days between a specified start date and end date. Of course, this necessarily includes weekends and holidays. The next thing I want to show you how to do is how to get rid of all the rows in which the entire row is missing. These are days which likely correspond to non-trading days. And even if they are not non-trading days, we can't do anything with these days anyway. As you may know, this can be accomplished by using the drop_NA function. But if you just call drop_NA without any arguments, it will not do what you want. Drop_NA will drop any row with any missing data by default. We only want to drop the rows where all the data is missing. So first we specify axis equals 0, which means drop rows and not columns. We say how equals all, so that only rows in which all data is missing are dropped. Finally, we say in place equals true, so that we do these operations on the existing data frame. Next, we plot the IBM close prices again, and at least the visible gaps which were pretty evident are now gone. We can check how many missing values are still in the dataset by using the isNA function. This returns a boolean in every location, true if the cell is NA and false otherwise. Recall that in Python, true equals 1 and false equals 0, so if we simply sum all the values, we should get how many missing values there are. If we call sum once, you will notice that it only sums along one axis at a time. So now we have the number of missing values for each individual stock. Since there are too many stocks to look at all at once, the next thing we can do is simply sum the result. So in effect, we call sum twice, and that tells us how many missing values there are in total. As you can see, there are about 17,000 missing values. Now, we know that any stock for which there is no initial value must be backwards filled. So let's try to figure out how many stocks fit that scenario. We can do so by checking how many stocks have a missing value in the first row of the data frame. That can be accomplished by using the iloc function. We call iloc0 to get the first row of the data frame. We call isNA to get a boolean for whether the data is missing or not. And finally, we call sum to get the total number of missing values in this row. As you can see, there are 29 stocks for which there is no initial value, and these are the ones which must be backward filled. As mentioned, before we do any backwards filling, we must forward fill. We can do that by calling the fillNA function. Saying method equals ffill directs pandas to use forward filling, and in place equals true means the operation is completed on our existing data frame. After we do this, we should check again to see how many missing values there are now. Interestingly, we see that a majority of the missing values from before are still missing. This indicates that many of the companies in our list are for some reason missing a lot of data from the start of this dataset. But recall that this dataset is from Kaggle. This may not be the case for the dataset we collected ourselves from Yahoo Finance. I've noticed that this was at least the case for Google. It's probably the case for quite a few other stocks as well, since Google has certainly existed long before the start date of this dataset. So how do we backfill? Well, we call the exact same function, fillNA, from before, except now we pass in method equals bfill. After this, when we check the number of missing values, we see that it is now 0, as expected. The next thing I'd like to do is plot all of our stock prices on the same chart. For this plot, I'm going to say legend equals false, since showing 500 items in the legend is a bit too much. I'm also going to set fig size equals 1010 so that we can see the plot more easily. So what do we see? Well, they look like a bunch of stocks, which is nice. There is at least one stock where we can see this backwards fill behavior, so it's this gray one over here. As you can see, there is over a year's worth of missing data for this stock. One common operation in finance is to plot the relative stock price over time. This allows us to more easily compare growth, or lack thereof, of different stocks. We can accomplish this by dividing each column of stocks by its initial value. Of course, the initial value divided by the initial value will become 1. And any subsequent value will be the ratio between the current value and the initial value. This allows us to easily see the cumulative return on each stock, which we will define more rigorously in another lecture. For example, when we see a stock on this normalized chart that goes up to 20, that means if we invested in that stock, our investment would have gone up by a factor of 20. So we can accomplish this normalization simply by dividing the data frame by the first row of the data frame. That's closeprice.iloc0. Note that broadcasting happens automatically, so there's no need to do a for loop. Finally, we plot our normalized prices. And in fact, we do see a stock that goes up to about 20. As an exercise, try to figure out which company this corresponds to.